my name is Sumantra, and this will be basically an introduction to image transforms. Why at all does one look at image transforms? The idea is to basically have the same data in another form, possibly for a more meaningful or a different interpretation. The related idea is compression. I'll come to that. And finally, we want a discrete case, that is, we want a digital computer interpretation. Now, how does one look at a transform? Now, all of us, at least those of us who have gone through an engineering degree, would be aware of transforms such as the Laplace transform or the Fourier transform, right? Haven't we all wondered why they all look similar? Most of them would have some sort of an integral. Okay, just let's just look at it philosophically. You have some sort of an integral, okay, in the continuous case. Then we'd have the original function, okay, and after that there would possibly be some negative exponential or some exponential function or something out here. There would be some function out here, and there would be a variable of integration. This is the original function. This is what is known as the basis functions, alright, or the set of basis vectors if you have a vector interpretation. And then finally what you get is a transform. Okay? In the case of a Fourier transform, why are electrical engineers so fascinated by the Fourier transform? Because the transform that you get out of it, f of omega, is minus infinity to infinity f of e to the power minus j omega t dt. Now this is one particular transform that has a neat frequency interpretation. Okay? That is, equivalently one can look at things in the frequency domain as one could look at it in the time domain. Alright, so this has got a very neat physical connotation, physical interpretation. This is one reason why one might like to use a transform. Okay? The corresponding thing in the discrete domain, okay, it's called a discrete Fourier transform, wherein the integral is replaced by a summation. That's the standard technique that we know. This is the original function. In the discrete domain, I have a negative exponential term. Okay, this is the notation that I've used. Yeah. So as you can see, this is pretty similar. Philosophically, this is pretty similar. Alright? So the idea is that if I have a discrete signal or image, for instance, a digital image, then I can get a Fourier transform out of it. I can get something that is meaningful in some other sense. Alright? But something important to realize is that, see, there are many different ways to look at a transform. This is just one of them. You might have read about something in the continuous domain which is Parseval's relation. Alright? The energy of the signal in the time domain and the energy of the signal in the frequency domain is exactly the same. That is, basically there is no information lost, no information created. It's just a different interpretation. Alright? That is the idea. And in terms, somebody in signal processing might look at a transform like this. This is the Fourier transform. And a person in mathematics would look upon it in a slightly different manner. One would look at a transformation as a change of basis. One would look at it as a change of basis, okay, in such a way that if I have a n-point signal out here, this is my original signal with n points, what I am doing is basically I am pre-multiplying that signal by a matrix which consists of a set of basis vectors. Alright? I can imagine this as a set of basis vectors either like this or like this, depending on what interpretation I give to that. And I get another signal that is of the same size. Now, any transform I can put in this form. That's something that's interesting. Okay? In the discrete case. What does this mean? if I have an original signal, this thing is very easily extended to images. So if I have an endpoint signal out here, this is my original signal f of x. Okay, and if I subject it to this particular transform, I get the Fourier transform, which is also an endpoint signal. If this is n, then this is also capital N. And this array is capital F of u, wherein u goes from 1 to capital N. In this case, x goes from 1 to capital N. Alright? I can look upon any transform in this manner. That's the idea. One of these ideas is to basically take it into some domain wherein we can have a better physical interpretation. A related idea is actually compression. I'll come to that when I have a couple of examples. In fact, we study so many transforms in our, typically the bachelor's program here is 4 years, right? We call the Bachelor of Engineering degree as a 4-year transform, wherein a person gets exposed to a lot of dirty math. Okay, so this is Fourier, and there's a transform named after him. Who is this? Yeah, this gentleman is Mr. Cosine. He's got a transform named after him called the discrete cosine transform. And as you know, for example, you've heard of the JPEG image coding standard. The basic JPEG had the discrete cosine transform, the DCT. Any idea as to who this lady is? She's the inventor of a very famous transform. I'll give a hint. This is Professor Ingrid Dabashe. And yeah, basically, yeah, she's the one who is credited with the invention of the wavelet transform. And one talks about gender equality or gender inequality. It's a lady who has perhaps the most fundamental transform in today's world, and she is credited with its invention. Okay, these are some transforms. There are some other transforms as well. For example, there's a Hadamard transform, there's a Walsh transform, there's a sine transform, there's a Haar transform, there's something called a Kale transform, and there are many such transforms, plethora of transforms. Okay, there's something interesting. One of the most fundamental algorithms that came about in the year 1965 was the discovery of two people who had a lot in common, apart from their first names, of course. Okay, they came out with an algorithm to compute the Fourier transform. Okay, I could get an image of only one of them, and the idea is actually pretty similar, pretty simple. Excuse me. If you have a look at the formula that's there for the Fourier transform, I have this on some corner of the board. Yeah, it's right here. Okay, so for a one-dimensional case, you can look at this formula and find out how many computations are involved. Let's look at computations in the order sense. Okay, number of multiplications, for instance, because multiplications are costlier than additions. How many multiplications do I need? Alright, how do I compute the Fourier transform? I'm given this signal. How do I compute the Fourier transform? How many loops would I need if I were to write this in a programming language like C? I need 2 loops. An outer loop would be for u equal to 1, u less than or equal to n, u plus plus. Okay, and of course I'd initialize f of u, I'd initialize to 0, and after that I'd have another loop for x, right? In this case I've written, oh god, that's bad notation. Okay, yeah. So for x equal to 1, x less than equal to n, and then what would I do? F of u plus equal to this particular computation. So how many loops? There are 2 loops, and each of them runs order n times. So the overall time complexity is order n square. So there are order n square multiplications. This is a very simple way to understand it. The other way to understand this is, See, I have each f of u needs order n computations. And how many f of u's do I have? Order n. So this is order n squared. This is relatively costly because the number of computations tends to grow as n grows. Now these two people, Cooley and Taki, came up with a very interesting algorithm which would reduce the time complexity of computations from order n squared to order n log n. Now n log n is obviously going to increase, the rate of increase is smaller than n squared. Alright, because log is a sublinear function. And the way they got it is actually pretty interesting. And can any of you guess what was the background of these people? That is one reason. See, I have been emphasizing that image processing is a multidisciplinary activity. So is algorithms. All of these are related. Can you guess what these people were? They were certainly not computer scientists. Okay, because computer science was hardly around at that point in time. They were not electrical engineers either. They were not mathematicians either. Can you guess? Yeah, I heard the right answer. Piche se, pretty close. Actually, it's close to math. They were statisticians. Okay. In fact, lots of people make this distinction. If you go to a statistician and say that, hey, hi, I never knew you were a mathematician, वो समझेंगे कि गाली दे रहे हैं. Because that, yeah, statistics is taken as a completely different thing altogether. Yeah, this is the formula that I wrote here. This is what I've written. And the idea is actually pretty simple. You know a simple way to show that these computations are order n log n as opposed to order n square? I think all of you would have heard of algorithms such as merge sort or quick sort for sorting. The idea is basically if I have an array of size n, right? So if I have to compute the fast Fourier transform of a signal of size n, I divide it into two parts. The even part, that is I take alternate samples. I take the Fourier transform of the even part, I take the Fourier transform of the odd part, and then I combine them. So if I have to write that as a recurrence relation, I can say that the time taken to compute the FFT of a signal of size n is the time taken to compute the FFT for the odd part plus the time taken to compute the FFT for the even part plus some time needed to combine them. That will be linear. You can combine two arrays in a linear time, right? Because you will have to read in each element. So this I can write as T of n is twice P of n by 2 plus Cn. Now how does one, we can unfold this recurrence. For instance, if I have an array of size 2, then it itself is its FFT. Or I can generalize it to time taken to compute the FFT of size 1 is a constant, maybe k or whatever. Okay? So I unfold this recurrence, and what I will end up with is Pn is something n log n, a constant n log n. So it's pretty easy to show. In fact, which term will the n log n come about? Will it come about in the first term or the second term? Any guesses? It will come about in the second term. Because if you unfold it, the next term will be Cn plus something, it will basically be n plus n by 2 plus n by 4 plus so on and so forth. It's basically like saying that if I have a rod of size n, of length n, into how many times can I split it so as to get unit length? It's always log n. Okay, because each time I am dividing it into half. That's precisely when. So this is one of the most important algorithms for the scientific community. And it can be extended to images as well. Okay, an image is just a set of, you can imagine an image to be a set of these arrays. Alright, and the algorithm is absolutely similar. And there's a property of a Fourier transform which is called separability, by which a two-dimensional fast Fourier transform can be computed using one-dimensional fast Fourier transforms. Then there is another transform that's called a K transform. This transform has been repeatedly invented and reinvented, and people call it names. Okay, some people call it the Arjuna-Lev transform. This gentleman who came up with the formulation, it's named after him, it's called the Hotelling transform. Many people know it as principal component analysis or PCA, but basically what it is it's basically an eigenvalue eigenvector transform. Okay, and it's interesting. This transform is said to be the optimal transform. Optimal in what way? We'll come to that. Optimal because, now look, now I'll give an introduction to where one can get data compression using transforms. Now one idea is I can look upon any transform as the following operation. Given the original signal f of x, I pre-multiplied by a transform matrix B, I get the transform signal f of u. Okay? Alright. Now one of the things that one realizes is normally signals are smooth or images are smooth. They do not have too many high frequency components. If you look at common images, you will see lots of constant or near constant intensity regions. Okay? So there will be a lot of low frequency components in an image. High frequency components come home. On the other hand, if you had things like a checkerboard image or let's say salt and pepper noise, you randomly put pixels as white and black. That would have more high frequency components than low frequency components. There is very little smoothness in it. But most natural images or most natural signals would tend to be smooth. Right? If you look at the waveform that's there in a radio program of music, for instance, you see a lot of smoothness there in it, as opposed to what happens, for example, when maybe you're listening to an AM radio and there's thunder crackling outside, there's lightning. Okay? There will be sudden crackling sounds on the radio, which would change very fast and then die off. They would be high frequency components. So most natural signals would have lots of low frequency components. So if this is the Fourier transform, I have basically split up a signal into its high frequency components and the low frequency components. And if I know that high frequency components are very few in number, then I can approximate them by zero. Okay, I can approximate them by zeros. So the high frequency parts I can as well make zeros. So the end result is out of an array of size n, often we'll find that most of the entities would tend to be very small, which can be approximated by zeros. So I can possibly take only L out of these components and have something that is an approximation of the original signal. How is that an approximation? I apply the inverse Fourier transform. I make these zeros. I apply the inverse transform and then get back something which is very much like the original signal or the original image. This is a form of lossy image compression or lossy signal compression. Okay, this tells you where compression comes in. Now there is something called the K transform, which is said to be the optimal transform, which says that if out of all possible transforms that I can have, out of all possible matrices that I can have, if I take only L out of the coefficients, then the error that I am going to incur is going to be the least among all such transforms. That is the K transform. Then why doesn't one use the K transform? JPEG में लोग DCD की बात क्यों करते हैं? Why doesn't one talk of the K transform? In fact, this can be proved. This can be proved quite easily. In fact, one puts it in a constraint optimization framework. That is, I want to minimize an error function subject to some constraints. One puts it in a, this is a Lagrange multiplier technique, one puts it in a constraint optimization framework. Maybe I want to have all of these basis vectors as having unit norm, -1. Okay, one wants to minimize these. So it will turn out to be an eigen problem because you are going to minimize it with respect to the parameters and also differentiate with respect to lambda. And then what you are going to get out of it is that lambda will turn out to be the eigenvalues of the system and the basis vectors will turn out to be the eigenvectors. That is precisely it. This is the KL transform. Okay, the KL transform is optimal, but then why don't we use it? Any guesses? Why do we use the DCT or the DFT? The answer is actually pretty interesting. In order to find out the eigenvalues and eigenvectors, you need data. And the eigenvalues and eigenvectors are data dependent. On the other hand, sines, cosines, exponentials, complex exponentials are not data dependent. They are fixed functions. So it's easier to use them in that sense. Okay? So that's why the KL transform is not very commonly used, although it's known to be optimal. Now, I'll be doing a little bit of cheating. In this case, what I'm not showing is exactly the KL transform, but I'm showing something related to it. It's basically trying to reconstruct something with a fixed number of eigenvectors, which is less than the total number of eigenvectors. There's something related called the singular value decomposition, but the basic idea is similar. So what we did was we took the image of a very famous model, okay, and tried to reconstruct that image using one eigenvector. Using 5 eigenvectors, let's see if you can identify that famous model. 10 eigenvectors, 50 of them, 100 of them. By now you should have identified them, right? And this is the original image, right? So that's it. So this tells you that you can actually get a lot of compression. And this actually happened to be compression in the real sense. This was before I got married. Has to be rather lean on the
So this PCA and ICA both are the same?
ICA is slightly different. ICA is independent component analysis. Well, it's got, you can put it in an eigenspace connotation, but since you've asked this question, independent component analysis is typically used in, for example, suppose there is an array of microphones. You have an audio signal, and what you want to do is a source separation. You want to say that this part of sound came from mic number 1, this part of sound came from mic number 2, and so on. In that case, you will typically apply independent component analysis. You assume, you make some independence assumptions, and then try to solve it. Otherwise, these techniques are actually quite related. One of them is PCA or eigenspace analysis. There is something called linear discriminant analysis, LDA, also called Fisher spaces. Okay? Then there is independent component analysis. All of these are quite related. Yeah, that's a nice point that you raised. Yeah, compression doesn't get as bad as that, video compression. But I'll talk about some things to do with video compression possibly tomorrow as well when I'm discussing motion analysis. Okay. This will give an idea of compression for 2D images. This is an image of a hornet. Okay? And this is its Fourier transform. As you can see that most of the coefficients, most of the non-zero coefficients of the Fourier transform are concentrated in the low frequency part. We have centered the Fourier transform here and drawn a couple of circles. So the zero parts are basically drawn with black and the whites are the non-zero parts. Now if I say that, if I have a bandwidth limited channel and if I tell the recipient, okay, I'm sending you a 512 cross 512 image, but I'm not sending it as such. I'm sending it as a Fourier transform and I'm sending maybe only the part that lies in a radius of, let's say, 10 pixels. Then, what is the recipient going to do? The recipient is going to create a blank image, 512 by 512, and then at the center of it, maybe paste only this information that comes in. The pixels in a radius of 10 and then takes the inverse Fourier transform. So the recipient should get something that looks like the original. This is lossy compression, but then you can look at the extent of compression. If you try to create a JPEG image using any image manipulation or conversion software, one of the things it will always ask you is a quality factor. If you put a very high quality factor, then the loss would be less. Okay, but then sometimes we are willing to tolerate. See, that's one reason why your JPEG images are much smaller than TIFF images, for instance, or BMP, which may be uncompressed. Okay, this is one reason. Yeah, motion image compression doesn't get as bad as that. And then, of course, there are industry standards. These are two terms that you would have heard of. JPEG, which stands for Joint Photographic Experts Group, and Motion Picture Experts Group. Now, why at all does one talk of standards? It's just like the ISI mark. Okay, there is a standardization. Research एक तरफ है और usability दूसरी तरफ. Sometimes things which have nice theoretical results are not very usable. So this try to standardize everything and get a set of industry standards which would be efficient, okay, and would also be reasonably easy to understand. So that there's some standardization, like JPEG and MPEG happen to be industry standards. And almost everybody today tries to conform to these standards. Of course, there's a plethora of image and video formats. In fact, all VCDs, any idea what the format is? It's MPEG 1. MPEG has got different variants, MPEG 1, MPEG 2, MPEG 4, you're talking of MPEG 7, 21, yeah, all of these are standards in the making. Okay, and there are some pretty interesting ideas in each and every one. There are other video standards like H.264, right? Then image formats, lots of you know about. Yeah, this is not the sort of peg that we're looking at, but just standards. Okay. Then the next topic that I'm going to talk about is image enhancement and restoration. No, not this sort of image enhancement, but enhancement in a sense is subjective. This is the difference between enhancement and restoration. In both cases, the input is a distorted image. Alright? And in both cases, one wants to get a nice image out of it. Now, that niceness could be subjective. So, image enhancement methods are subjective. Restoration has a proper mathematical model. For instance, there are some very good mathematical models for, okay, why don't we give cameras to little kids to take pictures? Well, nowadays, of course, there's something called image stabilization or camera stabilization, which is built in. Why? Because their hands tend to shake. There's motion blur. That's precisely the word that I was looking for. Absolutely. Now, there are some very good models for motion blur and very good formula to remove motion blur. Now, typically, this is posed as the following problem. If I have an original image, f of x comma y, right? This is subjected to some degradation process, okay, some transform on the image, plus some noise that's added to it, and what one gets at the output is another image g of xy. But this is typically, maybe I'll use some different notation. Maybe I'll use h out here, or script h. Okay, so this is basically, there is a model for the degradation. Like for instance, for motion blur, there is a translational model. Typically, the camera has translated. Okay, so there is a proper model for it. There are in fact some very good models for a couple of phenomena. And then what one is given is this. And the problem at hand is to estimate the original undistorted image. Okay, this is the way that one poses the problem. And this might be modeled as a convolution, so that would be in the frequency domain, that would be a multiplication. So you'll get f, capital F of u comma v as possibly g of u comma v divided by maybe some part of the transformation process, the degradation process. This is called direct. This is called direct. Sorry, what is it called? This is the degradation model. This is called, I think, direct inverse filtering. This is called direct inverse filtering. Okay, and the nature of this model tells you that this is noise prone. Why? If at any point in time the Fourier transform of the degradation model has very small coefficients, close to 0, this is going to blow up. This is not numerically stable. So there are some stabilization techniques. One typically puts in a constant. Okay, it can be shown that a constant, which is not too small, does not change the properties of the restoration and yet works reasonably well. Then there's something called optimal filtering. There's Wiener. The entire theory of Wiener filtering, okay, comes in here. Now, why at all does one look at such models? That's because in many cases, these models actually model reality quite a lot, like motion blur, that's one of them. Then atmospheric degradation. Images taken with a satellite which have got distorted due to atmospheric degradation. It's possible to get the undistorted images back. It's possible to estimate. That is image restoration. And that is not subjective. Why? Because there are proper mathematical models. Use in image analysis is to remove noise. Noise is typically high frequency components. Like if you're listening to an AM radio broadcast and if you look at the signal, when there is a lightning cackle, there is a sudden high frequency component. And what do you do to remove that high frequency component? You do low pass filtering. And I think we are all teachers, right? I can share a secret that some of us electrical engineering teachers often do. What happens if the class makes noise? You threaten the class with low pass filtering. In the frequency domain, I was there at IIT Bombay for about 6 years, and one of the common visitors to the campus, there in the papers is a panther. Okay, a leopard that somehow seems to manage to come in almost every time. And what do you do when you see a panther? Shoot it with the camera, of course, and then take its Fourier transform. Okay. Now, in this case, you would see that there are quite a few high frequency components, like a sudden change in gray levels here. So you see some high frequency components. Okay. Now, low pass filtering is basically, for example, this is blurring. Oops, wait a sec. So what I have done here is taken only the low frequency components, zeroed out the rest, and taken an inverse Fourier transform. So what this has done is this is smoothed out. Okay. So one can experiment with various radii and various levels of smoothing. Okay. So this is also image compression in a way. Right? You can see that with a high radius, not complete, you can get something that looks like the original, just an inverse Fourier transform. Okay, there is another low pass filter. Like most people in signal processing are familiar with Butterworth filters or Chebyshev filters, depending on what sort of things you want for the pass band, for the stop band, what sort of things you allow. So a Butterworth low pass filter has got a slightly more elaborate mathematical formula for it, and limiting cases can be shown to, like when you increase the order of the filter, then you can show that it goes towards an ideal filter. There are some advantages, there are some disadvantages. Okay? Like an ideal low pass filter is associated with effects such as ringing, which are not, that's because you are suddenly cutting off a set of frequencies, and Mother Nature abhors sudden events. So you pay for it in terms of a ringing effect. Okay? That's basically what the difference is. Okay, you can also do low pass filtering in the spatial domain by using a mask. This is basically a two-dimensional convolution wherein you take the signal, flip it around not one axis but two axes, and then move it all around. Okay. This is an image of a person whom we recognize. This is the original, and this is a noisy version of the same image. Now this is a motivation for non-linear filtering. Suppose one wanted to do linear filtering on this using a mask. Simple low-pass filtering. With a mask of a particular size, one gets this. N equal to 3. Increase the size of the mask, one gets a smoother version, but no. There were some original high frequency components in the image, sudden discontinuities, which got lost in this transition. Alright? Sometimes this does not work too well. Okay? So instead of the mean, which is basically a smoothing operation, why not take the median? Computational cost is more because it involves sorting. You sort the number of elements, take the middle. Okay? So you can get some example like this. That depends on the noise distribution, of course. Okay? And it might be interesting. What happens if you increase the size of a median filter, the neighborhood? This is n equal to 3. This is n equal to 5. This is n equal to 7. Now you might have seen some image display or image processing software which claim to give you an oil painting version of the original image. Believe it or not, it's as simple as a median filter. All that they're doing is they're applying a median filter and possibly applying some jitter on top of it. That's all. It's a pretty interesting effect, but the underlying theory is very, very simple. High pass filter. Just as low pass filtering was an averaging operation, high pass filtering is a differentiation. Okay? Alright, these parts I'll quickly skip through. And again, our human visual system also has high pass filter. For example, it's been shown through psychophysical experiments that if at any point in time we enter a new surroundings, let's say a new room, the first things that are going to catch our attention are points of discontinuity, like the ceiling and the wall, the division there, or the point where two walls meet. It's been proved by psychophysical experiments that these are the first things that catch one's attention. So this is effectively our human visual system is simultaneously doing low pass filtering as well as high pass filtering. That's interesting. Okay? So one has heard the parable about a leopard and its spots, right? So you can actually separate out the spots from a leopard using high pass filtering, because these are essentially high frequency components. Okay, so just a couple of experiments here which I'll run through. Just as there are Butterworth low pass filters, there are Butterworth high pass filters as well, and one can play around with the parameters. As before, what parameters to use, that completely depends on the application. Okay, there's no set of rules. You can say that, okay, for these sort of things, I need these set of parameters. No. Okay, a bit of math which I'll just quickly run through. Alright, there's something called high boost filtering, wherein one takes an image, one takes a high pass filtered version of the image, and then takes a linear combination of the two. One can get some startling effects like this. So this basically accentuates edges.
So this is same as L-sharp masking?
In a way. In a way, yes. There's a lot that's related. For example, okay, another way to look at this is instead of adding to the original image a high pass version of it, is take the image and subtract a smooth version. Okay, there are lots of these basic things here. And there are some spatial domain enhancement techniques as well. There are some algorithms which rely on neighborhoods and some which rely on the entire image as such. Like taking the negative, that's a linear operation, then stretching the contrast. Okay, the slope, this is something like a transfer function. So had this been a 45-degree line, the input would have been equal to the output. Now you want a linear relationship, a piecewise linear relationship, yet you want to accentuate some regions. Okay, this means that for a small change in the input, there would be a large change in the output. That is typically used, for example, in the Fourier transform. Typically, most signals would tend to be smooth. So they have most of their non-zero coefficients in the low frequency region. They can make values in all come. So what one might like to do is stretch the contrast for viewing pleasure. That's all. Something called dynamic range compression, Gray level slicing, I won't go through that. There's something called histogram processing. Okay. There are dark images, there are bright images, there are low contrast images. See, low contrast images could be very bright or very dark. And there are high contrast images. Now, often what we want to do is increase the contrast. For example, this is an image of Mount Rushmore. This is the histogram. See, most of the gray levels are concentrated in a small region. What we want to do is to spread out the gray levels. Okay? Spread out the energy among all gray levels. This has better contrast. Okay, in this, the gray levels are spread out much more. Look at this image of a set of flowers, and this is a histogram equalized version of that. Okay, when I was in IIT Bombay, there was this lab called the SPAN lab, where there was a camera, there was a webcam that used to be on day and night, and at night, one day in the lab, there was a person who came in. Okay, he was captured on camera. Now after that, we actually found out the person after doing histogram equalization of this image. Okay, so basically I had a class in the morning. I needed a printout desperately, so I came to the lab at night and I got shot on camera. I was caught and shot. Okay, yeah, this is what I've talked about. Essentially, in image restoration, there is a model for degradation, okay, as opposed to image enhancement. Yeah, this is it in the Fourier domain. Convolution, the equivalent thing is multiplication, and generally one assumes a additive process. Depends. One can have a multiplicative noise model as well. There are some signal processing problems, especially in optical signal processing. That's what some of my friends tell me, that multiplicative noise models are more natural. I don't know why. Detecting features from images. One can find out things like edges, lines, corners. Okay? And edges are basically high-pass filtered elements. If you join edge points, you can get a line. And intuitively, a corner is a place where there is a change in intensity along more than one direction. One direction, it's an edge. Okay? If in an image there is a black stripe and a white stripe, there's an edge in between. There's a sudden change in intensity. Okay? If there is a change in intensity along more than one direction, this is along one direction, then what you get is a corner. It can be detected with a reasonable degree of comfort. For example, this is an image, this is a calibration object, and what I've marked here are the lines superimposed and the corners. You can see this better if I increase the contrast. Here. Should be visible? Then image segmentation, a simple thresholding is also an example of image segmentation. Segmentation, you want to split an image into different regions which have something in common, like a similar texture or a similar color. For example, in this case, here we have done an image segmentation and replaced each region by the mean color in that region. Okay? So, these are operations which one can perform automatically on images. Find out edges, find out corners, find out different image regions, segmentation. So, what's the moral of the story? If one wants to have an edge over others, one must not think in terms of cutting corners. But also one needs to know when to draw a line. I draw a line out here and move over to the next one. That is reconstruction from projections. Okay, if one has projections, there is something called a Fourier slice reconstruction theorem. Helps us get reconstruction from projections. I think this image will tell you what we are talking about. What sort of projections, which is slices of the human body and then putting them together. One is talking about what? In medical terminology, what is one talking about? Where? Yeah. It's a CAT scan, a CT scan, it's called it. It doesn't get as bad as that. But it's interesting, I was looking about on the net, and in the Royal Ontario Museum, they had this mummy of a lady called Jed Patterson, and using CT scans, they were able to find out things about the mummy which could not be found out had one not opened out the mummy in a destructive manner. Alright? For example, they found out that the lady had died out of a dental cyst that had suddenly burst out. They were able to find out by doing CT scans on various layers. They were able to reconstruct facial features, okay, from the mummy itself. Like in the case of, like National Geographic had this on its cover a couple of years back, in 2005, they had tried to reconstruct Egyptian Queen Nefertiti, or I've forgotten her. Cleopatra. They tried to reconstruct Cleopatra. But that was from other evidence. In this case, they have a mummy. And you want to reconstruct facial features without cutting open the mummy. Right? And some artifacts on the body itself. It's possible to do so using CT scans. Right? And these are things that, yeah, they could find out things like this. And see, these are things that you cannot do. For example, you could afford to put that high level of radiations on mummies. Like otherwise, you put a human being with that high level of radiation and you might end up mummifying him or her. Right? So you can put these techniques to lots of good use.